All right. Good morning, everybody. Sorry. um, okay, so some of you, I think about 7 of you, should have seen it jump in your exam score by 4 points. There was one question I decided there's nothing wrong with it. I decided it was a little nitpicky. You thank Maria. She caught it. Not here right now, but she could. There she is. I was just telling everybody that a couple of people got a boost in points because of a question that she saw. There's nothing wrong with the question. It was the one on ionization energy. And I was getting confused between ionization energy and electron affinities and the sign when I was talking to Maria, but the question's okay. It's just a little nitpicky. So there was 2 answers that were pretty good. So there was, I think, 7 people that had that question and put this one answer, which I gave people credit for. So about 7 of you should have saw your score go up by 4 points. The rest of the answers were fine. If you put one of those, they were just wrong. All right. So where we're at is going to knock out chapter 4 and possibly start chapter 5 to see where we're at, where we're going. We've introduced Lewis structures. We'll do more of those as we go through, but I got some other stuff to cover. Resonance is just something I'm going to talk about. It's important you're exposed to it. If you see a question on an exam, it'll be one question, real basic. I don't really typically ask this. But I did want to talk about this a little bit because ozone's really important. Ozone's in our stratosphere, right? And it's protecting us from ultraviolet light. And scientists just reported recently that the hole this year is particularly large. There's an ozone hole that forms every single year over the South Pole. Mask up for me, please. Thanks. Over the South Pole. And so people in New Zealand, or Australia, have to be careful during their spring or fall because the sun is so strong, the ozone hole is so thin at that point that skin cancer, we have documented epidemiological information about skin cancer. There's much higher prevalence down there. And this is because of chemicals that we've put up into the stratosphere that destroy the ozone, called chlorofluorocarbons. And I talk about this stuff in my environmental chemistry class, and we go through all the chemistry because this is Nobel Prize chemistry, so it's fantastic chemistry. So ozone, and a couple things that happened just recently is that, well, that's related to climate change. I want to go into that. But anyway, we've done a pretty good job of phasing out some of these chemicals that deplete ozone. The problem is the ones we replace them with are horrendous heat trapping gases, which leads to climate change because of warming, because they trap all the heat. So the Biden administration just announced, or like yesterday or today, they're phasing out some of these chemicals into our refrigerants that are super heat trapping gases, way more than CO2. And this will actually have a substantial impact in lowering that temperature increase that we're expected to see over the next decades. But ozone is what we know as an allotrope of oxygen, which means it's only composed of oxygen. That's what we mean by an allotrope, okay? Carbon has multiple allotropes. There's diamond, there's graphite, and there's Buckminster fullerene. That's the one that looks like buckyball, soccer ball. They're all composed of carbon. They just have different structures, right? Same thing here, O2 and ozone, just composed of oxygen, but they have different structures, obviously. So this is ozone. And you can see you could write 2 different Lewis structures for this, and they're basically the same, right? Just depends on where you put the double bond. What's interesting is that we know from experimental evidence that the bonds between this oxygen and this oxygen are exactly the same. Okay? Exactly the same. We know from both measuring the length of the bond and from the energy of the bond. So the question becomes, what's going on? And what people like to do, they call this resonance, is to say, basically put a double arrow like this. And it's a little tricky because it's not like the bond fluctuates in between and goes back and forth. it's, this is where weird kind of quantum mechanical stuff comes in. It's almost like when you mix yellow, I'm terrible with colors. When you mix yellow and red, you get orange. Do you still have yellow and red? Are they switching back and forth to form orange? So it's almost like you have like a bond and a half between each of these oxygens or something. We don't necessarily really know what's going on, but the fields between these two oxygens are the same. How do you explain that? How the electrons, remember, it's a wave, it's not a particle. Okay, so perhaps there's some sort of, interaction between the waves that creates an interference that creates two fields that are identical. Who knows? So I wanted to point this out to you. And anytime you have this type of situation, you can draw resonance structures. You're supposed to put an arrow in between to show that. But and here's the example where it shows you the length of the bond, and that length is somewhat in between a double and a single bond. I thought the numbers were on this slide, but I forget. Maybe they're on this slide. No, they're somewhere in your book, where I think the oxygen single bond is maybe, bigger than the 128. The oxygen double bond is less than the 128. You get the idea. Okay, so that's just to expose you to resonance. Probably won't see anything on your exam. Occasionally one pops up on a final exam. Oh, here it is. That's the slide I was looking for. So a double bond is 121 and a single bond is 148. Typically what we measure. So it's just showing you that this is neither a double or single bond, okay? And this is where, kind of quantum mechanics, quantum theory gets a little weird, and we just have to accept it because this is what the experimental evidence tells us. All right, so now we're going to use this idea of formal charge to decide which structures are correct, because there's going to be cases where we can draw different types of structures. So here's N2O right here. And there's three structures here. And all of these kind of seem to be okay, right? Nitrogen has its octet and oxygen has its octet in all three cases. Now, oxygen likes 2 bonds and nitrogen likes 3 bonds, but those are just general guidelines. And on the left here, well, nitrogen's got 3 bonds, but oxygen's only got 1, and that one nitrogen in the middle has 4. But the one on the left, oxygen has 3 bonds, right? The one nitrogen has 4, and the one has 1. The one on the right, oxygen has 2, but one of the nitrogens has 4, and one nitrogen has 2. So which one's correct? There's no violation there of Lewis structures. They all have the same number of electrons, okay? They've all got their octets. So the question is, which structure is correct? And we're going to use this idea of formal charges to answer that question. Just keep in mind, this is not really real, okay? Mask for me, please. That's okay. It's once again our kind of accounting system to try to sort of keep track of things and come up with a way to figure this out. I don't know, it's a representation. Okay, don't take it too literally, but it helps us by using certain rules. It helps us to figure out how this structure's gonna. What I mean is that the charges aren't real. The answer of the structure will be real. We know that from experiment. Now we know what the structure is. Okay, that's what I mean to say the charges aren't real, if you will. Okay, and bear with me, you'll see what I mean. Okay, so let's take a look at how you do this. So what you're going to do is determine the formal charge for every atom in the molecule for all 3 of the molecules. Okay, and the way you do the formal charge, you take the number of valence electrons for the atom, you subtract the number of lone pairs, okay? No, I'm sorry, the number of electrons in the lone pairs. So a lone pair would be 2 electrons, 2 lone pairs would be 4 electrons, number of electrons in lone pairs, minus half of the shared electrons. See, the idea is the shared ones are split evenly between the 2 atoms. That's why you're taking a half. Okay, so for here, that's a shared pair of electrons. One of those electrons goes there, one goes there. That's the idea. It's just really just an accounting system to help us figure this out. And if it's a lone pair, well, then they go completely with that atom. Okay, those two are going to go with this nitrogen there. Okay, that makes sense because that's the only one that's got those electrons. Okay, so the formal charge will be the total number of valence electrons for that atom minus the electrons in the lone pairs and half the shared ones. And you're going to do that for all the atoms in the molecules. And here's what you get. So this is the table that shows you the calculation. So let's just take a look at that first nitrogen here. So the valence electrons for nitrogen, that number is going to be the same all the way across. It's 5. And for oxygen, it's 6. So the top, once you figure that out, the top numbers are the same. Nitrogen's 5, oxygen's 6. That's just the group number, right? 5 and 6. Okay, so number of lone pairs, lone pair electrons, well, there's 2 that get attributed to that nitrogen, so that's that 2 there. And then it gets shared electrons, 2, 4, 6. It's going to be half of those though, right? So I don't know why they did it like that. They should have put a 3 there. So I guess they're doing it down here. You're going to take half of the 6 and the 2. So half of the 6 is 3. So basically wind up with 5 minus 5, right? That's where the 0 is coming from. 5 minus 5. Did everybody see that? Okay. And you do that for all the atoms. I'm not going to do it for all the atoms. Does everybody see how I got the 0? Okay. You do that for all the atoms. Now, 3 criteria to use now to determine the best structure. Sounds like a lot of work, right? If you got one of these on an exam. But it's not that bad because usually it's going to be like, hey, what's the correct Lewis structure for this? And you're going to come up with maybe 2 options. And then once you get good at this, you'll quickly figure out on just one of the atoms, it's going to be key. You know, you'll see that as we do this, as we do more Lewis structures and how we use it. So this one's a big table with 3 structures just to kind of expose you to it. But in many cases, you'll simply look at the formal charge on one atom in like 2 structures, and that'll help you decide. Okay, the best structures are one in which the formal charge on each atom is 0. You want zeros, okay? That means the structure is more stable, okay? If you go back and look at that, start to talk about how that 0 means and all that, we don't need to do that. Just trust that right now that's the way it works based on the way the lone pairs and the valence electrons are, because the valence electrons are an indication of the bonding capacity, right? That Lewis dot structure and the number of valence electrons and the number of lone pairs and shared electrons is tied into that bonding capacity. So that's why this works. If no such structure can be drawn, the best structure is the one where most of the atoms have formal charges equal to 0 or close to 0 as possible. Could be negative or positive, but close to 0. So which means -1 is better than +2, okay? And +1 is better than +2. Close to 0 is possible. Any negative formal charges should be on atoms of the more electronegative element. So another way of saying, okay, well, the more electronegative ones like electrons more, so if anything, they should have more electrons close to them, which is going to make their formal charge negative, right? You don't want a negative formal charge on a carbon that's bound to an oxygen, right? Because oxygen is going to grab those electrons, and that's going to be the one that's more negative, if you will. Okay? So, that being said, which is the best structure here? Who said that? A, right? What's your first name again? Talia. Talia says A, and she'd be right. Well, we can get rid of this one. It's got a 2 and 2 1s, right? These 2 are similar, but the negative we want on the oxygen, not the nitrogen, because oxygen's further to the right, has a higher electronegativity. If you remember, it's the only element with electronegativity of 3.5. Fluorine is 4, oxygen is 3.5, and then chlorine and nitrogen are the same at 3.0. So that is correct. So this is our correct structure. Question. So that's, in some cases, I'll ask you a question on the exam and say, what's the formal charge on the atom in this Lewis structure? In other cases, there might be just a Lewis structure where this is going to help you decide what the correct Lewis structure is. It won't be a question to ask about formal charges, be a tool for you to use.
Relating to the Lewis structures, why does that one have like a triple bond, a single bond, and then double bonds, but the three oxygens just have the double bond and single bond when you were showing the ozone?
I'm not following your question. It's a different molecule. In this case, ozone. Are you suggesting there should be resonance in this?
I'm just confused on why that one. Usually, like the middle one doesn't have any electrons. Like it doesn't have any dots, and so
that's not true.
It's not.
It is something like carbon, yes. But nitrogen, take a very simple molecule like ammonia. That's a Lewis dot structure for ammonia. So you're probably relating maybe to group 4. Most of the time, carbon, silicon, those ones that form 4 bonds don't typically have electrons around the central atom. But heck, water's got electrons around the central atom, right? Got 2 pairs. So when you're in groups 6 and 5, you're going to have some typically electrons around the central atom. Not always, just depends. Does that help? Other questions? Okay. All right. Now there are exceptions to the octet rule. Okay, and these are exceptions that are important you need to recognize. They're not similar to the exceptions we did with electron configurations. There's a couple ones that I think are important that you should know. So not all atoms have complete octet when forming bonds. Beryllium, boron, and aluminum are your classic examples. And there you see boron trifluoride. It does not have an octet. Okay, it's just the way it is. If you go on and take organic chemistry and things like that, you'll probably get into more molecular orbital theories, some of the stuff that we're going to introduce in the next chapter. They'll start to explain what's going on more about orbitals and why things like this happen, but that's just not the topic for this class. It was too advanced. In fact, we're not even doing this whole second half of chapter 5. There's no time for it. And it's what the department decides is, up through Vesper, maybe a little bit of hybridization some of us do, and that's about it. And the rest of it we leave for organic. They don't like it up in organic, but most of them have never taught Gen Chem. And I keep telling them, until you teach Gen Chem, don't tell me what to teach in it, because they want us to do all this stuff to prepare them for organic, not realizing how much stuff we have to cover. And I'm sure you guys don't want more material. All right. The other one is greater than an octet. Some atoms can accommodate more than an octet of valence electrons. They typically bond with strongly electronegative elements. So you see sulfur hexafluoride here. This occurs when the expanded shell produces a structure whose atoms' formal charges are close to 0. This is where you'll get a feeling for how formal charge can help you decide. And it should be on another slide, if not here. Okay, there it is. It's only going to happen for elements in the 3rd row or below. Why? Well, that's where the d orbitals start. Where the heck is nitrogen going to put all these bonds if nitrogen did this? That's only 5. You can put 6 there. Nitrogen can't do that. There's no orbitals available to it. You got to have the orbitals, right? Okay, even though we're going to take atomic orbitals and change them to molecular orbitals, hybridizations, things like that, you still have to have that availability. So once you get down to group 3, that's when D starts. Even though the periodic table shows a big gap there, because they don't fill at that point, doesn't mean d orbitals aren't available. Quantum mechanically, they're available once you get to the 3rd period. That is the 3rd energy level. Okay, so sulfur has 3 d orbitals available to it. And that's why it can accommodate extra expanded octet. Atoms of nonmetals in the 3rd row and below can have an expanded octet. PCl5, SF6, SO4 2-. Atoms will expand their octet when they bond with strong electronegative elements. Said that already. An expanded shell produces a structure whose atoms' formal charges are close to 0. Kind of said that already also. Questions? So it's just a matter of start recognizing them. That's all. As you do more and more, I've had numerous, which is a good thing. Just would have been better if it happened after the first exam, but I've had numerous, and I have more coming up. Zoom sessions and meetings in my office with students over the last couple of days, which is good. So the next exam is going to require you to do a lot of structures. Because it's open book, open note, and you don't have to be here, I can't just ask, what's the lowest structure, because you can Google it. While most of you are honorable and have integrity and won't Google something because you were told that it's wrong and it's cheating, I've done this long enough to know there are students that will not follow that rule, that will do what they need to do to get the grade. And it's for those students that I have to protect the integrity of my class and my exam, which means the questions have to be structured in a way that can't be Googleable easy, which means you could have something like, which of the following structures has one lone pair around the central atom? And now you have 5 structures you have to look at and potentially draw, or at least quickly be able to delineate that answer. It's very difficult to Google. You've got 5 structures. You'll spend more time Googling than just doing the structure. And you'll get wrong answers when you Google. So just be aware, you've got to do a lot of practicing of structures for this exam. So let's do one right now. What is the Lewis dot structure for SO4 2- ion? Does this ion have resonance structures? So we're going to follow the rules now. The steps, not rules, but steps. What's the first thing we want to do? Valence electrons, right? Valence electrons, we don't care about core electrons, just valence. How many valence electrons here? You get quick at doing these. Oxygen's in group 6, so 6 times 4 is 24, right? So sulfur, group 6, so it's 6 times 5, right? Got 5 atoms, all in group 6. Group 6, that's 30. What do we do with that 2-? 32. You caught your own mistake. Good. You add them because that's an anion that's got 2 extra electrons. So we have 32 valence electrons. Everybody see where we got these 32 valence electrons? Okay, what's my central atom? They're in the same group. What's my central atom? Sulfur. Why'd you choose sulfur? 4 oxygens plus, it's further down in the periodic table, which is usually the rule because it has the potential for an expanded octet if we need it. And they're often, another one is, they're often written in the way the central atom is first. Okay? Not always. You'll just see different people write things different ways, but often the central atom is written first. But when you got 4 oxygens, right, you got 4 of the same, it's usually you got a central atom and then 4 surroundings. So we're going to do this. Okay, and I'm going to attach the atoms. Okay. Now I got to complete the octets. 8 times 4 is 32, right? We got 4 attachments, so and now with ions, you usually put a bracket with a 2 minus 2 around it. I'm going to hold off on doing that for a second. Does everybody want to stop here? You think we're done? Now we're out of electrons, right? Okay. Let's just play a little game here and calculate the formal charge on sulfur, and see what it is. What's the formal charge on sulfur? 6. What is it? Plus 2. Herschel's right, she's plus 2. How'd she get that? Well, 6 valence electrons minus it's got no lone pairs. So that's the 0 plus half of the 2, 4, 6, 8. So 4, right? Half of that. Everybody got that? Equals 2, right? Everybody see that? Yes, no, yes, we're good. Any questions where the 2 came from the formal charge on sulfur? The what?
The 8.
What 8? Oh, 2 for each bond. 2, 4, 6, 8, right? And then half of that, you take half of the bonded pairs. That's the 4. Other questions? That's not a particularly good formal charge. What are they on oxygen? They're all going to be the same. What are they on oxygen? Very good. Is that Andrew that said that? Andrew says -1. What did he do? He said formal charge is equal to 6 minus, it's got 2, 4, 6 all to itself, and then half of the 2, which is 1, plus 1. Now we have a -1. Okay. Heck, we could probably do better than that. By doing what? Where's that coming from? Adding a double bond. Yes, we can add a double bond. Sulfur can take an expanded octet. So let's go ahead and take one of these here. All right, get rid of that. And then just put a double bond there. What's the formal charge become now on the oxygen that we just changed? 0, right? 6 minus 2, 4, 5, 6. That's the other way to do it. I don't even do the half. I just count the 2, the ones that are low, and I go 2, 4, 5, 6. I do 1 for each bond. That's the way I do. That's why I don't put it in the formula and go half of the dough. I mean, once you get good, you just count them up like that, right? So this is now 0. So this is a 0 formal charge. What's the formal charge on sulfur? It'd be plus 1, right? It's going to decrease by 1, and the oxygen went up by 1. So it's now plus 1. And maybe we could do it again to another oxygen. And then that oxygen will be 0, right? And the sulfur will be 0, right? And there's your answer. Do it again, and you have your answer. You don't want to go further than that, because now your sulfur will be -1. So that's how you know to stop. You see? This is the beauty of formal charges. Now I can stop. Because 2 of my oxygens are 0, the sulfur is 0, and the other 2 oxygens are -1. They're the more electronegative ones. So that's okay. We can't get better than that. Because if we do another oxygen, we're going to wind up with a sulfur that is -1. And that's no good, because that's not the more electronegative element. Yes.
So if you have a compound with like multiple elements around the central atom, like is there a certain way to know which one you add the double bonds to, or is it just trial and error?
It doesn't matter, because this has resonance anyway. And that's part of the question. So here's your final answer, 2 minus, and it's going to have resonance. All those bonds are the same anyway. So for us, it's just a Lewis structure. It doesn't matter where you put the double bonds, anywhere you put them is correct.
Okay, so even if you have like another element other than oxygen,
Well, another element besides oxygen.
yes.
Okay, so it depends what the element is. So if it's chlorine, no, chlorine typically doesn't like double bonds. So you'll have to do the structure and decide on the formal charge on that chlorine, whether it could take a double bond, but more likely than not, no. But if it's like selenium or something like that in that group, same group, it's going to do the same thing. It really depends on the structure. And that's what you'll get a feel for the more you do. And the formal charges will help answer that question for you.
So with the original Lewis structure before you modified it to be more correct, that wouldn't have resonance to this, right?
No, because there was no double bonds.
Okay.
Right. So this one actually can, because this double bond could be here or here. So you got, where you have resonance structures. Questions? It's a great example. I like to do this one simply because you get comfortable doing Lewis structures. The example of Lewis structures, just to see how formal charges can lead you to the correct structure. And you can see why you've got to be comfortable. I've talked to a lot of students, like I said, over the last couple of days, and what's come to light, which is the case lots of times, is that they seem to know the material, just doing it in 80 minutes or 85 minutes, you make more mistakes, right? It's not the same as working at home. You will do a problem. Yeah, I got that right. You took 20 minutes to do one problem. Okay. Right? You don't have that kind of time when you take an exam. So it becomes second nature to you. You got to do a lot of them. So you get a structure like this right off the bat. Sulfur is a central atom. 6 times 5, 32 valence electrons, bond around each one. You get quick at doing them, and you get real comfortable. Questions? Let's do the hydrazine molecule. How many valence electrons? 14. So in this case, there's no real central atom, right? Because you got 4 atoms, but the nitrogen's a better central atom. So and the hydrogens are peripheral. So you might want to just, say, okay, something like this, right? Two hydrogens off of each nitrogen. So how are we doing? So we've got, if we did this, we got 2, 4, 6, 8, 10, 12, 14, right? So what are hydrogen's going to have a formal charge of 1 always, because it's always got 1 minus half of a bond, so it's always 0. Always 0, not 1. What's the formal charges on nitrogen here? There's 0, right? So we've got 5 minus 1, 2, 3, 4, 5, and they're both the same. This looks good to me. You don't need double bonds, right? Right? We've used up 14 electrons. Looks good. That's all. Okay. Questions? There are odd electron molecules, and that you might have figured out because in some cases, when you add 2 together, you get an odd number. And nitrogen and oxygen is an obvious example because 6 and 5 is 11, even if you had, formal charges will lead you to the answer, but which one gets that single electron, but also The one that's more electronegative is going to like more electrons, and that's the one with the octet. So in this case, nitrogen doesn't get an octet. It only has 7 electrons. But there's not much you can do about that. The formal charges are worked out for us already, and they're good. So you just have that single dot on the nitrogen because you have an odd number of electrons, and it has to go somewhere. One of them has to be deficient. And since oxygen is more electronegative, the nitrogen winds up being deficient. If you did put the single one on the oxygen, do your formal charges, and you'll realize it's not the right structure. This one's the better one because you got 0 and 0 formal charges. So nitrogen's one of those key ones. You see it also with some of the halogens because they're odd, you know. Those are the 2 big ones when you look at, you know, the molecular compounds we form a lot of. You know, it's going to be groups 5 and 7 that are the most prone, those elements most prone to having, because they're odd numbered, having a single electron. So we call these radicals. They're extremely reactive, as you might guess. You might know free radicals from like health, right? The free radical scavengers. So, you know, vitamin E, certain materials are free radical scavengers, things like that. We also have a lot of radicals in the atmosphere. They're formed as a result of high energy cosmic rays that hit molecules of gas in the upper atmosphere. And that's enough energy to dislodge electrons, things like that. Radiation is what we call ionizing radiation, X-rays, things like alpha particles, beta particles. These are called ionizing radiation. Why? Because they can dislodge electrons from matter, and that can be dangerous because they become very reactive. They can destroy tissues and things like that in your body. So the radicals can be important in both health and atmospheric chemistry, things like that. So this is the last slide of the chapter. And so one thing that's interesting is that you guys all know that matter interacts with electromagnetic radiation. That's just what we talked about in quantum theory. That's the only way you were able to see anything, detect anything with all the instruments upstairs that we use. We got all different types of instruments, but the basic premise of all of them is some sort of electromagnetic radiation is used to basically detect something. Anything you want to know what something is, and that's what I mean. There's plenty of instruments where you're not identifying something that's unknown that don't require any electromagnetic radiation, just chromatography separating things, you know. So CO2 absorbs infrared radiation. It is. So here's the Earth, right? And here's our sun. And radiation comes in, and it's mainly visible, some infrared, some ultraviolet that comes in. Most of the other stuff gets filtered out because the sun generates everything. X-rays, microwaves, cosmic rays. But a lot of that gets filtered out up here in your upper atmosphere by the ozone layer and other things, right? Then what comes off of the Earth is infrared radiation mainly. That's the radiation you feel as heat. Okay, you sit next to a fire, that's IR. You feel it. That's warm. The human body giving off IR. Okay? Well, CO2, we know, absorbs infrared radiation. It's a heat trapping gas. That's the greenhouse effect. That is been going on before humans ever walked the planet. That is a natural effect that is key to the Earth being a habitable planet. Okay? Without it. Okay, water is the other heat trapping gas. Those are the 2 big ones. Now, water is just part of our normal hydrologic cycle, right? Just, you know, evaporates and precipitates down, so the amount doesn't change on the planet. But we're adding more and more CO2, which is trapping more and more of this heat right here, and that's what's leading to the climate change and the problems we're having. And this talks about, you know, vibrating, and that's the way the molecule moves when it absorbs the IR. So whenever you use your microwave at home, what you're doing is you're causing water molecules to oscillate. That's what warms up your food. That's why if something's really dry, you're supposed to add, you know, having water in there is better. Too much water can be a problem, like soups can sometimes, splatter because they superheat, things like that. It's because of the water that's what you're doing. That's how you're heating something, is you're causing the water molecules to rotate. So that's the type of stuff you find interesting that you get to learn more about as you go on in your science career. As much as I'd like to spend more time on that, this class is really designed to be fundamental so you can go forward and take my environmental chemistry.